Okay, so that it sounds like the recording is working. Okay, welcome back everybody to our to the N3AS seminar. We are very happy to have Wouter Dekens speaking to us today on Neutrinoless double beta decay and effective field theory. So please, whenever you're ready, we're very happy for you to start.
Okay, yeah, thanks, Jeff. So yeah, I'll be talking about Neutrinoless double beta decay. And this will be based on work done with quite a few people over here. So yeah, Neutrinoless double beta decay, just to remind you, is a process in which a nucleus decays, emits 2 electrons, no neutrinos. So this would violate lepton number by 2 units. And the current experimental status is that, well, there are already very stringent bounds on the half-lives of this process. So they go up to 10 to the 26 years or so. And in the future, this is set to be improved by 1 or 2 other orders of magnitude in the next generation of experiments. So if those experiments would measure a non-zero signal, then this would tell us, for one, that neutrinos have to be Majorana particles. And another thing is that, well, it tells us that there has to be beyond the standard model physics that causes the lepton number violation. So then you can think about what kind of beyond the standard model physics this can be. So one often considered scenario is that Neutrinoless double beta decay could be caused by light Majorana neutrinos through a diagram like this, where basically you exchange light Majorana particles. And if that is the mechanism that's responsible, then Neutrinoless double beta decay should tell you something about the mass hierarchy of the neutrinos. However, in many models that generate lepton number violation, you also get additional mechanisms that can contribute to Neutrinoless double beta decay. So for example, in left-right models, you will have diagrams like this, where you exchange a bunch of heavy new particles. And so this would give you a new contribution that's qualitatively different from this light Majorana exchange. And since there are many models of new physics, each coming possibly with different mechanisms, we thought it would be a good idea to basically try to set up a framework that can capture any scenario of heavy lepton number violation. So that's more or less what I'll be talking about. And the basic idea is that we assume that there's some heavy scale that I'm going to call lambda, which will be the scale of new physics, above which there's some beyond the standard model theory that involves lepton number violation. And then below this heavy new scale lambda, we can integrate out all the new heavy particles. And this should give us an effective field theory that consists of the standard model plus higher dimensional operators. And then we can start to evolve this theory down towards lower energies. So first towards the electroweak scale, and then further down to the scale where QCD becomes non-perturbative. There I'll want to match this theory onto a theory in terms of nucleons and pions as degrees of freedom, for which I'll be using parallel effective theory. And then that, in combination with many body methods, should then finally give us an expression for Neutrinoless double beta decay half-life in terms of the Wilson coefficients of all these new higher dimensional interactions at high energies. So that's basically the plan of this talk. So yeah, I'll start by saying something about this effective field theory. So yeah, the form of this effective theory will be basically the standard model plus a bunch of higher dimensional operators. And it turns out that if you insist on the gauge symmetries of the standard model, then all the lepton number violating operators only appear at odd dimensions. So the first one will then appear at dimension 5, and this is the so-called Weinberg operator, which gives rise to Majorana masses for the usual left-handed neutrinos. Then the next set of operators appears at dimension 7. Turns out there are 12 of those that can contribute to Neutrinoless double beta decay. And then finally, at dimension 9, there are a bunch of operators which consist out of 4 quark fields and 2 leptonic fields, which can also give rise to Neutrinoless double beta decay. And it's only more recently that people have constructed a complete basis of these dimension 9 operators. So these are basically the operators or the interactions that I'll be taking into account, assuming that all the lepton number violation is heavy. But more recently, we also started thinking about theories or scenarios in which some of the lepton number violation could be caused by light new degrees of freedom. And one often considered well-motivated example of that are sterile neutrinos. So we thought it would be interesting to see what happens if you try to include sterile neutrinos in the same framework. And in order to do that is we basically add 1 degree of freedom to this whole effective field theory framework. So you add sterile neutrinos, which now have a kinetic term. They also have a Majorana mass term, which occurs at dimension 3 here. We add a direct term, mass term for these sterile neutrinos. And then in addition to that, you can think about, again, higher dimensional operators that now involve standard model fields, as well as this sterile neutrino. And you can think of those as arising from heavy new physics that couples to both the sterile neutrino and standard model fields. Yeah, so these are basically all of the interactions I'll be considering during this talk. But for most of this talk, I'll focus on the interactions that arise from purely heavy new physics. But once in a while, I'll say something about these sterile neutrinos as well. So then once we've written down our effective field theory below the scale lambda, this high energy scale, we can start to evolve this thing down towards first the electroweak scale. So here we'll want to integrate out the heavy standard model fields. So to give you some example, for the dimension 5 operator, the Weinberg operator, above the electroweak scale, this looks basically like a coupling between leptons and the Higgs field. And then below the electroweak scale, it will look like a contribution to the Majorana mass of left-handed neutrinos. And the dimension 7 operators, these induce below the electroweak scale dimension 6, 7, and 9 interactions. So the dimension 6 and 7 interactions basically look like couplings between 2 lepton fields and 2 quark fields, with or without a derivative. And then if you, by exchanging W bosons, you can also generate dimension 9 operators. And then finally, the operators that look like dimension 9 above the electroweak scale still look like dimension 9 operators below the electroweak scale, which look like interactions between 4 quark fields and 2 leptons. Yeah, and so this is what you get for if you assume that the lepton number violation is purely heavy, but you can do a similar matching for the interactions involving sterile neutrinos. Those look very similar to these dimension 7 interactions, basically. So then we can evolve these interactions towards even lower energies. So to the scale where QCD becomes non-perturbative, so QGeV or so. And there we'll want to go from a theory involving quarks and gluons as degrees of freedom to one involving nucleons and pions as degrees of freedom. And so the way to do that is to look at your quark level theory and consider the symmetry properties of the interaction in that theory, and then try to construct all the operators in the chiral Lagrangian that transform in the same way. And once you do that, in principle, you end up with an infinite set of operators in your chiral Lagrangian, and each of these operators would come with some unknown constant that should capture the non-perturbative part of QCD, basically, which we call low energy constants. And so for this chiral effective theory to be useful, you need some power counting scheme. You need some way of telling which of these interactions you need to include and which of them can be neglected to a certain precision. So I'll start by assuming the Weinberg power counting, sometimes called naive dimensional analysis, as a power counting scheme. And then I'll come back later whether this was a good idea or not. So yeah, I'll start with the simplest example of this matching, basically, which is the case of the light Majorana mass for left-handed neutrinos. So both the quark level theory and the chiral theory will have neutrinos as degrees of freedom. And so both of them will have this Majorana mass term. But in order to get contributions to neutrinos double beta decay, you also need some form of the weak interactions, which at the quark level look like the Fermi interaction. And then in the chiral theory, it looks like a Fermi interaction between nucleons and leptons plus pion exchange, basically. And then this Weinberg power counting would tell you that to leading order, these are all the interactions you need to include. And in principle, this is nice because it turns out that all of the low energy constants that are associated with these vertices here, they're known from experiment, basically. So that's positive. We know all the hadronic stuff. So then you can, after constructing this chiral Lagrangian with these interactions, you can start to construct diagrams using those interactions. So for the Majorana mass term, basically what you get is a diagram like this that allows you to go from 2 neutrons to 2 protons with 2 electrons. So this gives you basically a lepton number violating potential between nucleons. And then this could be, you can use as basically the starting point for many body calculations that would take this amplitude at the nucleon level to an amplitude between nuclei that are used in experiments. So this is the case for the Majorana mass term, but in principle, you can do basically exactly the same thing for all of these higher dimensional operators. So for these dimension 6 and 7 terms, instead of having the lepton number violation in the mass of the neutrino, you get lepton number violating vertices that look more or less like this. Whereas these dimension 9 operators induce a few different interactions in the chiral Lagrangian. So they can induce contact interactions between nucleons, as well as interactions between nucleons and pions, as well as couplings of just pions to leptons. And in principle, all of these interactions would then come with their own low energy constants. Now, for several cases, for several of these vertices, the associated low energy constants are known. So in these cases, a bunch of these low energy constants are known from experiment, basically, or lattice calculations. And for this mechanism involving pions, there are also lattice calculations available. So those are also known, those low energy constants. But for these two mechanisms, basically, these low energy constants are, at least at the moment, unknown. Nevertheless, you can then take all of these interactions, construct a potential like this, and this would then be the starting point for these many-body calculations. However, as I mentioned before, all of this stuff was basically based on this naive dimensional analysis, or this Weinberg power counting. And it turns out that this power counting already breaks down in just the strong interactions. So usual QCD in certain cases. So we thought it would be good to check whether it makes sense for neutrinos double beta decay. And in order to check this, what we tried to do was basically compute the simplest amplitude. So we picked the case of the light Majorana mass. And then the simplest amplitude would be taking 2 neutrons to 2 protons with 2 electrons. So that's more or less this diagram, but dressed with strong interactions. Yeah, so in order to do that, you need some form of the strong interactions, which in chiral EFT, just at leading order, just look like a contact interaction between nucleons plus pion exchanges. So then you can start to look at all of the dressing the lepton number violation with all of these strong interactions. So one type of diagram you would need to compute are basically dressing the lepton number violating vertices with any number of pion exchanges, which is what these blue blobs are. And then at some point you have to start adding in these contact interactions as well. Now, most of these diagrams are finite and there are no problems there, but at some point you encounter diagrams where you insert these contact interactions on both sides of the lepton number violating vertices, and then you start finding divergences. So for example, if you compute this in dimensional regularization, you find basically a 1/epsilon pole, so a divergence, and your amplitude starts to depend on the regulator. So yeah, mu in this case. So yeah, if you plot then the amplitude as a function of your regulator, in MS bar, you basically get a straight line. It's a pure log dependence, of course. But in principle, you can also look at what happens if you use a different regulator scheme. So we also tried seeing what happens if you use a cutoff regulator, and you basically see the same thing. So at least in some range for this cutoff regulator, you also see basically a log dependence. And so this means that, well, we have an amplitude that depends on something that's unphysical. So it cannot be a physical amplitude, basically. And the way to fix this then, at least in chiral EFT, would be to add in an additional interaction. So in this case, this would be a contact interaction between nucleons and leptons, which would come with a new low energy constant, which I'm calling G nu NN here. And now the point is that according to the Weinberg power counting, this type of interaction would appear at next to leading order. But what we're finding here is basically that in order to get an amplitude that's renormalization scale invariant and doesn't have any divergences, we need to include this thing at leading order already. So once you add this, you can redo the whole calculation and check that everything can be made renormalization scale invariant, and that works out. So that means that at least the amplitude could be a physical thing. So that's positive, of course. The negative thing is that you've now introduced a new low energy constant, which you don't know from experiment. And so you have something that's unknown, but you would need to know in order to predict Neutrinoless double beta decay half-lives. So preferably you would get this thing from a first principles calculation, which so that would be a lattice calculation basically, and people have started looking into this. But this is a pretty complicated calculation. So at the moment, at the moment, what we have are estimates of this low energy constant. And we've tried doing this in several ways. So you can look at a comparison of this low energy constant to very similar low energy constants that appear in isospin breaking observables, or trying to model it. And people have looked at large NC estimates, and they more or less agree, at least, that that this low energy constant should be something of order 1, which would mean that it would be a leading order effect. Right. So this is basically what happens for this Majorana, Majorana neutrino exchange. So that's to say that in addition to this this diagram that people usually include, you would also need this new contact interaction. And then you can go back and repeat the same analysis for all of these higher dimensional operators as well. And then it turns out that for several of these higher dimensional operators, you also need additional contact interactions in order to ensure that the amplitudes are finite and renormalizable. So after doing that and modifying the power counting in some cases, you end up with a chiral Lagrangian with a number of interactions from which you can build these diagrams. And these diagrams then basically give you a lepton number violating potential, which you can use as a starting point for these many body calculations. So let me say a few words about those. So it turns out that if you want to be able to describe all of these mechanisms from these higher dimensional operators, then there's only a fairly limited set of nuclear matrix elements that you need to know. It turns out there are 15 of them. So I'm showing some numbers here in some units. And the nice thing is that chiral EFT predicts some leading order relations between some of these matrix elements. So you're able to check that these relations, whether they're satisfied by the results in the literature, and they tend to agree to 10 to 20% or so. So that's at least encouraging. However, if you then compare these nuclear matrix elements as computed by different methods, then you find that they can vary by factors of 2 to 3, depending on the matrix elements. So here you see on the x-axis a number of different matrix elements for different isotopes, and the different colors are basically different many-body methods. So at least at the moment, that gives you in most cases, an order 1 uncertainty on your prediction of the Neutrinoless double beta decay amplitude. Now, a hopeful thing is that the ab initio methods or calculations have started to appear, also for nuclei that are relevant for experiments now. So these ab initio methods used to be constrained to lighter nuclei, but now they're starting to appear for nuclei that are used in experiments. And then the hope is that at some point, these types of calculations could not only provide you just a number for the matrix element, but also an error bar, or at least a reasonable uncertainty estimate. And then hopefully at some point, this factor of 2 to 3 starts to shrink somewhat. But yeah, for the moment, there are significant uncertainties related to these matrix elements. So this is basically the whole story that we need for these high-dimensional operators, assuming that lepton number violation is heavy or rising from heavy new physics. And in principle, you can go through exactly the same steps if you want to include the sterile effects from sterile neutrinos. So yeah, you basically have to go through the same tower of effective theories. The main differences are that, that things now start to depend on the mass of the sterile neutrino. So the simplest case is basically whenever the sterile neutrino is heavier than about a few GeV or so, because in that case you can integrate it out already at the quark level, and you usually end up with an operator that's basically a dimension 9 operator that I already talked about. However, if the sterile neutrino is lighter than a few GeV, you basically have to keep it as a degree of freedom also in the chiral effective theory. And then low energy constants, as well as these nuclear matrix elements, start to depend on the mass of the sterile neutrino. But in principle, you go basically through the same steps as before. Okay, so then using all of that, we can start to do some phenomenology and start to see what kind of constraints we can set. So if we again assume that lepton number violation comes from heavy new physics, in particular, assuming that it comes from these dimension 7 operators above the electroweak scale, then what this means is that their Wilson coefficients have to scale like 1/λ cubed. And using that assumption, I'm basically showing the bound on the scale of new physics that you can set using Neutrinoless double beta decay. And what you can see here is that for the operators that look like dimension 6 and 7 operators below the electroweak scale, you get constraints of up to a few hundred TeV or so, whereas the operators that look like dimension 9 operators below the electroweak scale, they go up, their bounds go up to tens of TeV, basically. Now you can do the same thing for the operators that look like dimension 5 operators above the electroweak scale. In those cases, their Wilson coefficients have to scale like 1/λ to the 5th. And so you get weaker constraint, but still in the range of 1 to 10 TeV or so. And of course, I should say that these constraints are subject to these order 1 uncertainty due to low energy constants and nuclear matrix elements. So this is what you can say if the lepton number violation is heavy. we can also look at what happens if you include these sterile neutrinos. So one thing that which we tried was basically a toy model where you have the standard model plus one sterile neutrino with a Majorana mass. So then what I'm plotting here is the half-life of neutrinos double beta decay as a function of the Majorana mass of the sterile neutrino. And then what you find is this red line here. So at some point you see that the half-life flattens out due to the sterile neutrino decoupling, basically. And then what we were interested in was to see what the effect is of adding these higher dimensional operators involving sterile neutrinos. So that's what you see in green here, which is basically the same scenario, but now we add a dimension 6 operator that involves this sterile neutrino and assume a scale of 10 TeV or so. And this additional interaction would allow a new contribution to neutrinos double beta decay half-lives through a diagram like this. And it turns out that, if you look at this plot here, then you see that especially for masses of the sterile neutrino just below a GeV or so, you can get a huge enhancement. So these higher dimensional interactions, they can be important. And then more recently, what we tried looking at was the interplay between neutrinos double beta decay and single beta decays. So whenever you have sterile neutrinos with these higher dimensional operators that contribute to neutrinos double beta decay through diagrams like this, you also get contributions to single beta decays through, a simple diagram like this. As long as the sterile neutrino is light enough. And so, one thing we thought that would be interesting to look at is what neutrinos double beta decay can tell you if these single beta decay experiments find a signal or non-zero signal of these higher dimensional operators. And fairly recently, people have done an updated fit of a bunch of single beta decay experimental data. So this includes neutron decays, but also decays of nuclei and mirror nuclei in this paper here. And this turned out to be more or less perfect for a thought experiment, because it turns out that if you do this fit to all of this single beta decay data, the fit turns out to prefer slightly prefer a non-zero value for one of these sterile neutrino interactions. So that's what you see in this plot here. You have two interactions of sterile neutrinos. So these are dimension 6 operators. And you see the blue region, which is the preferred region, is at non-zero values of the CT minus, which is basically a tensor interaction between a tensor interaction involving sterile neutrinos. You shouldn't take it too seriously, because this anomaly is basically driven by one experimental result. And it's unclear if you can really construct a model that can give you this preferred region without being excluded by collider data already. But nevertheless, for our thought experiment, this is more or less perfect. So if let's say that in the future, single beta decays experiments confirm that you have some non-zero value of this higher dimensional operator, then that means that you should get contributions to neutrinos double beta decay as well, as long as you have a Majorana mass for these sterile neutrinos. So then you can draw, if you assume some value for the sterile neutrino mass, you can draw exclusion or the allowed area that's allowed by current neutrinoless double beta decay experiments. So here the solid line is what you see, is what you get currently. And then the dashed line would be allowed by future experiments. So then you can see that by the next generation of experiments, assuming that you get this dashed line here, you would be able to say that the only way that neutrinos double beta decay and the single beta decay experiments are consistent with one another is if the mass of the sterile neutrino is lighter than 30 eV. So another way of saying it is that whenever these single beta decay experiments pinpoint a non-zero value for one of these higher dimensional operators, then neutrinoless double beta decay becomes a very sensitive probe that gives you an upper bound on the Majorana mass of the sterile neutrinos. You see it's pretty stringent. It goes down to 30 EV or so. Yeah, so that's more or less all I wanted to say. So just to summarize, I hope I managed to convince you that EFTs are useful in describing a whole bunch of lepton number violating interactions. Yeah, in order to get an expression for the neutrinoless double beta decay half-lives, you have to go through this whole tower of effective theories, where the most complicated or interesting steps are basically the matching to chiral EFT and these many-body methods. But even though at the moment these come with significant uncertainties, yeah, neutrinoless double beta decay is still a very sensitive probe, probing high scales of depending on the operator that's responsible for neutrinoless double beta decay, it can probe up to 1 to hundreds of TeVs or so. Yeah, that's it. So thanks for your attention.
Okay, great. Yeah, thank you for that incredibly interesting talk. Let me give the clapping hands here, assuming I can make Zoom work. Okay, very good. All right, so let's go into the question phase, and I see that Susan has her hand up.
That was a lovely talk. It was really interesting. I actually have a couple of different questions, but let me just start with the one that I think is, let me just start. In particular, if I introduce a right-handed neutrino, I may give it a Majorana mass, but I'm not sure I'm compelled to give it a Majorana mass.
Oh, sure.
And so I guess I just wanted to point that out because I think, let me just give an advertisement to, I think something, maybe Jeff mentioned in one of his recent news sessions that were just for our collaboration, but there's lovely, interesting experiments that look for sterile neutrinos in nuclear beta decay using quantum sensing techniques to reconstruct the kinematics of the final state, and thus limiting through missing momentum the possibility of a sterile neutrino. I personally find them fascinating. There's BEST, and there's Hunter, and various nuclear targets. And of course, if we give the right-handed neutrino Majorana mass, then the constraint that you speak of, vis-a-vis the non-observation neutrinoless double beta decay, exclude those experiments by many decades. However, I think that it's very interesting to think about all possibilities. And I guess my question has evolved into a comment because I'm just pointing out that you've assumed that the right-handed neutrino has a Majorana mass.
Yeah,
but,
no, that's definitely true. Yeah, you're right, of course. If it doesn't have a Majorana mass, then neutrino's double beta decay doesn't say anything. That's true. Yeah.
So I'm going to ask a question. I'm very fascinated about the prospects of new ab initio nuclear matrix elements potentially redressing the factor 2 to 3 differences when we possibly, and I just wanted to know what insights we get from the latest, because it's a historical result that there's variations in matrix elements by factors of 2 and 3. And I wonder, within the context of the new ab initio methods, what you think the emergent picture might be, given that there are several papers out already.
Yeah, so I think it's still fairly early to tell. Yeah, I think those calculations, at least in their papers, they also say that they still have work to do to really get a good estimate of their error bars. But I think what is consistent between those calculations is that they tend to find smaller matrix elements than, for example, the shell model. So it's on the smaller side, seems to be.
Okay, well, I even asked more, but I see that someone else wants to ask a question, so I'll let him talk. Thank you very much.
Okay, Sanjay, go ahead.
Hi, Wouter. Thanks for that nice talk. I have a naive question. You basically talked about the need for these new counter terms to ensure renormalization. And the question is, so that spoils the simple relationship between a nuclear matrix element and the scale at which you'd expect new physics. So by how much does it spoil it? So what is the uncertainty in identifying the scale of new physics because of the need of this new term required by renormalization?
So, so I think from the estimates we have at the moment for this new contact interaction, it seems like, yeah, it would be more or less an order 1 effect. It depends a bit on your estimate, I guess, but yeah, it would be an order 1 effect. And then depending on what you assume, the new physics, how it originates, oh, sorry, going the wrong way. Yeah, that basically determines what the uncertainty is on the scale of new physics. So I mean, if you assume that it's due to a dimension 7 operator, then yeah, these Wilson coefficients scale like 1 over lambda cube. So at some point, yeah, if you want to extract something on the scale of new physics, you have to take a cube root, right? So that so in these plots in these bar charts, for example, the effect might be mild, right? Because, well, you have to take a cube root at some point, and there's a log scale. So
okay, so
in that sense, maybe it's not so bad, but
yeah, so that's what I was trying to understand. So if you want to put error bars on these bars, there wouldn't be a big deal unless there's some model building effort in high energy physics that really needs to know where that is. Is that a correct interpretation?
Yeah, so I think the main point is that in order to, let's say you do measure something, then in order to get a fundamental physics parameter out, you need to know these matrix elements. But yeah, I would agree that in order to set, if we're just at the stage of setting constraints, then probably you can live with well, I mean, you probably would still like to do better than a factor of 2 to 3, but yeah, if you're plotting things on a log plot, maybe it's not so bad.
Okay, thank you.
Okay, and we have a question from Wick.
Sorry, I was muted. It's a really great talk. I just have, first of all, a comment about what Susan said. There's an old theorem due to Schechter and Baye that shows that if you have double beta decay, then you generate Majorana neutrino mass. So I think there is a really intimate connection between seeing double beta decay and having at least the Majorana component in the neutrino. My worry more about this is the kind of philosophy of attacking the problem in this way, because this is very similar in some sense to dark matter. That you can work at any number of very, very high energy scales and then try to reduce down to where the measurements are made. But as you go up in scale, of course, you introduce more and more irrelevant constants that are unknown. So that approach is really motivated if you know the high energy physics well. But if you have a particular model, for example, that you favor and you want to see its low energy consequences. But like in dark matter, we're in a situation here where we really don't know anything about the mechanism because we haven't seen any neutrinoless double beta decay. So why not formulate the problem from the bottom up instead of from the top down? Why not work at the nucleon level, actually the non-relativistic nucleon level, because there are a very small number of possible operators you construct and do the expansion 1 over the nucleon mass, find out how many observables there actually are to disentangle if you happen to get lucky and make measurements in several nuclei with different properties. And then you're done in the sense that any theory, any higher scale theory that you want can be reduced to those relatively small number of effective couplings.
Right, sure, yeah. In principle, yeah, I think you could do that. I think the advantage of starting at the high scale is that in principle, you have connections to other observables. So this going through all of these steps of starting above the electroweak scale and so on. So for example, in the case of the stellar neutrinos, it tells you that you might be able to measure something in single beta decays and so on. I think that's probably a connection you would lose if you start at the lowest of energies.
Yeah, I'm not sure about that. If you're working at low energy, single beta decay is also a low energy process. So if you formulate an effective theory at that scale, whatever connections exist should emerge from that.
Well, sure, but then
in fact,
but maybe maybe I'm missing how you would construct the operators at low energy.
You write down an operator expansion and you associate with each operator an LEC, and then you find out how many such operators and therefore how many LECs have to be calculated. In dark matter, there are exactly 6 nuclear response functions that are allowed by CP and parity, and therefore you know that all you can measure in dark matter are these 6 low energy constants. And then everything else that appears at higher energy scales has to reduce to those constants. But it seems to me it's always the most efficient way to go when your physics is fundamentally unknown, instead of going from the top down where you have to start over again every time you introduce a new UV theory. You work from the bottom up. You finish your job, and based on whatever data is available at that time, you have your constraints, and then anybody can match to that. And so in dark matter, for example, various groups like the San Diego group and others have built interfaces at higher level that just talk to the non-relativistic effective theory formulation. And so there's actually kind of a cascade of different codes now that are all intertwined and talk to one another so that you can go through this process very efficiently. Now,
Yeah,
it can work for double beta decay as well.
Yeah, I think the point here is that in principle, this whole framework would allow you to, once you have your favorite model of lepton number violation, you can match it on at the high scale, and then the rest of it should be done. The whole point is that you don't have to redo those steps. So basically, they're done for once and for all, basically.
Yeah, at the low scale, you have all the experimental information, you have all the content of the experiment extracted properly at the lowest scale that you can operate.
Yeah. But so in this sense, like everything below this scale lambda would be the low energy stuff that can be done once and for all, basically.
Yeah.
And then so that's the point, basically, that you don't have to redo those steps each time. I think by starting at above the electroweak scale, for a certain operator, in certain cases, it does tell you something. So basically, the restriction of the standard model gauge symmetries do tell you that there are certain operators that shouldn't appear below the electroweak scale. So it cuts down the set of operators that you can have at low energies a bit.
Can I abuse my my position as host just to inject a perspective on this? Just the way that the way that the scheme of effective field theories is often framed is as either you take a bottom-up approach or a top-down approach, and it seems that this scheme kind of finds something, a middle-out approach, in the sense that the steps of getting from this high-ish scale, but not the ultimate high scale, to the nuclear scale are, at least in principle, well prescribed. Right? I mean, clearly we've heard that folks are working on this line of thinking. And then if one can establish this trajectory down from the middle and then adopt a model independent perspective from the middle, or if one wants to connect high scale to the middle to the low scale, then I think this is the scheme that we've heard about. And again, it's kind of an alternative to either top down or bottom up, I suppose. But anyways, I said I've abused my position as the host.
Middle way, Jeff. It's a middle way, right?
Exactly. Yeah. It's breaking down this false binary thinking, I suppose. But and this is all a little bit tongue in cheek. Anyways,
Jeff will send you to Ukraine next.
Yeah. Oh dear. I'm afraid I would be less than useless in that situation. Anyways, I've derailed us. So it looks like the next question it goes back to Susan then.
Yes, I just wanted to, not to make too fine a point of it, but I would like to suggest there are different kinds of bottom-up constructions we can consider. So rather than just think about an effective theory at the nucleon level, some non-relativistic one, as Wickus was suggesting, that I would propose to you, just to illustrate the potential pitfalls and the limits that we see in this figure. Imagine we extend our Lagrangian at mass dimension 4 level with couplings to new particles, such as captured in theories with color sextet scalars, or generally scalars which carry baryon or lepton number, which can each engender a new dimension 4 interaction with standard model gauge fields and be standard model gauge invariant, but yet can be sewed together at dimension 9 to make a short distance mechanism for neutrino double beta decay. So that's what I mean by bottom up, that I'm adding new dimension 4 interactions with new kinds of particles. So when I put that kind of theory together to build the associated coefficient with a dimension 9 operator, I have different particles. And I may have the product constrained by the experimental limit on the double beta decay rate, but the individual ingredients are not similarly constrained, so that you would end up having discovery prospects, say, for lighter mass objects that are with maybe something much heavier that could then be combined and constrain or match the experimental constraint of neutrino double beta decay. So the purpose of mentioning this is just to illustrate that although as interesting as these limits are, there are ways of defeating them in which you would have discovery prospects at lower energy. So I just wanted to point that out because I think it's very interesting and may be completely right, but maybe thinking about loopholes are also interesting. So that's I think it's a comment, but if you have something to say in response, I'd appreciate it.
No, I mean, yeah, that's definitely true. So the effective field theory we were using is basically this standard model EFT. And then you really assume that all of the new physics is heavy, right? So that's an assumption that you can break in principle. So one type of light field we tried adding is the stellar neutrino, but yeah, in principle, there are other possibilities which aren't captured by this whole framework.
Thank you very much.
Okay, and the next question is from Lucas.
Oh yeah, actually, so yeah, I rather have a comment, but I think that it was basically said already by Wouter, right? That I also perceive it as more like a framework that it's connecting, right? The low energy observables with possibly some high energy observables, and then that you can compare actually limits, for instance, coming from neutrinos double beta decay with limits coming from the LHC or yeah, colliders in general. And then I had one more comment related to Sanjay's question, right? Wouter, when you were showing these limits on the new physics scale for different operators, and Sanjay asked about the uncertainties. Yeah, those would be suppressed by the power of lambda that appears in the for different operators, but also I think maybe at least for dimension 9 operators, I think the major uncertainty would be coming then from unknown LECs, right? That maybe those would affect things even more than the nuclear matrix elements actually, and so that's
yeah. I think in principle for all of these operators I'm showing here, there would be in most cases there are unknown low energy constants and these uncertainties due to nuclear matrix elements. So yeah.
That's something that must be also taken care of by lattice people or someone, right? Or it may be even more important when it comes to these contributions than the nuclear matrix elements themselves, maybe.
Okay, and looks like the next question goes to Vincenzo.
Yeah, hi. Well, it was I had a couple of comments, but the things I wanted to say, they've been said already by Lucas. And it's basically, I wanted to reiterate that this philosophy of top-down versus bottom-up, if you don't start, I mean, I think, I use that as a guidance. I mean, if we believe that QCD is the theory of strong interaction, we should at least start with a quark level theory, whether you start above the electroweak scale or at the QCD scale, about 1 GeV. Otherwise, we lose a lot of connections. We lose, for example, I'll do the classic example of the beta decay, right? So for the longest time, constraints on tensor currents were obtained only by nucleon and nuclear beta decay. It turns out if you go one little step up to the quark level, it's the pion decay, it's paradiative pion decay that gives you the strongest constraint on the tensor operator, the tensor current. And there's no, I mean, I've never seen a model that will induce a nucleon tensor current and not a pion, the effect of the pion. So we need to, I think I strongly advocate for at least, whether you want to go all the way to electroweak, it depends on your taste or what degrees of freedom we want to include. But I think starting at the quark level is a minimum requirement to take into account the fact that QCD is the theory of strong interaction. But I understand that at some point it might become a matter of taste, but I just wanted to reiterate that point.
Okay, and the next hand I see is Daniel.
Hi, Wouter, how are you? Can you show your tower of EFTs again?
Sure.
I always enjoy it.
I don't know if it's big enough. You mean this thing?
Yeah, hang on a minute. Yeah, that'll work. So I want to lean a little bit on what happens below a GeV. So we already had a bit of discussion about this in the context of how much nuclear matrix elements and their uncertainties affect the bounds on lambda. Mm-hmm. But I'm going to suggest that it might be worse than that, because when you run down from a GeV to the scale at which you implement a nuclear many-body method, the running mixes the 1 and 2 body operators and introduces nuclear scales into the prefactors in a way that, at least to me, it's not entirely clear that how much the ultimate operators remember their RG boundary condition at a GeV. So I wondered if you wanted to comment on this problem.
So I think, so when I said that if you look at these constraints, that maybe on the log plots, you don't see that much of an impact. So, I mean, that's just, yeah, I think that's purely due to, what I mean by that is just, it's mainly due to the scaling of 1 over lambda cube and the fact that there's a log, right? I wouldn't.
So you're talking about the log in the 2-body matrix? I mean, so I think the problem is that you've got to do this when you run down, you're running down against nuclear wave functions which have anomalous dimensions, right? Mm-hmm. And so the question that I have, and it's really just a question, right? I don't know the answer, right? But the question is that when I do that running down from, let's say, nominally a GeV down to some sort of shell model scale, and I'm running with ab initio nuclear interactions that have anomalous dimensions, the scalings you put here just set the boundary conditions for that running. And so if that running gets overwhelmed by the running that comes from integrating out nuclear degrees of freedom, then the relationship between nuclear matrix elements and bounds will be more subtle than, I can take a cube root. So as I said, I just wanted to get your take on whether this was a concern or not.
I'm not sure if I understand. I think the scaling will remain the same. I think the only difference is that that at some point the thing you're taking the cube root of what the uncertainty on that number is.
But you're assuming that you're assuming that you can, what am I trying to say? This is like I'm asking a more complicated version of Sanjay's question, right? If the one and the two body operators mix, let's suppose things are really bad and you run so far down that the two body operator becomes dominant, right? And forms the dominant piece of the nuclear matrix element, right? And then the two body operator has all these, nuclear scales that come from integrating out modes above the scale of the many body method that you want to use. Then the connection between the nuclear matrix element and the 1 over lambda cubed is much more opaque, right?
I'm not sure if I'm understanding correctly, but I think so basically what I'm saying is that as long as I turn on one of these dimension, so in this case, I was looking at these dimension 7 operators, as long as I turn on one of those, then in the end, the amplitude should be proportional to 1 over lambda cubed.
So you're saying as long as there's one and only one,
yeah,
then whatever effect I get has to be proportional to that, because if this wasn't on, I would get 0.
Yes.
Okay. If there was more than one effect, then this could be a concern.
Then you can get cancellations and so on.
Yeah.
Sure. Yeah.
And figuring out how to disentangle between the two would require me to know, what had happened to the prefactors as I ran down.
No, sure.
Yeah.
The amplitude would still scale as 1 over lambda cubed if I assume that I'm just turning on dimension 7 operators. But yeah, you're definitely right that you can have all kinds of cancellations between.
Or I could have one that, a priori is small here that runs, that acquires a much larger value by running, right? Or they could mix, or all sorts of things could happen, right?
No, sure. Yeah. I think, the relation, I guess it's definitely true that once you measure Neutrinoless double beta decay, a non-zero signal, then it's going to be complicated to interpret, to really pin down what mechanism caused it.
To evolve back up, right?
The way back up, yeah. It's going to be
okay. All right. So I suspect I may just have set up Wick's comment, but we'll see how we go. Go ahead, Wick.
Yeah, I agree with that comment, Daniel. I also just wanted to reply to Vincenzo. I think he made a cartoon out of my comments. I certainly wasn't saying that once you found the LECs at the low energy level, that you ignore everything else at the high energy level. I'm just suggesting that what has happened in dark matter, I think, is a much better model for this problem than always working from a top-down point of view. Here now we have really nice codes that take us from the nuclear level and the nuclear constants that are defined that match on to codes that take you to the light quark level. And then with Solon and Hill, Susan's colleague, from there up to the Z scale. So you can make contact with what we've learned from CERN. And it all works beautifully, and it's more efficient because you have experts in each of the different interfaces doing the best they can. In particular, I think this connection between light quarks and the nucleus is profoundly difficult to do correctly, and is largely not done. And you can see it really simply because the integration that one does to come down to a light quark interaction is done in a momentum basis. And yet the only translational basis that we have for bound states in nuclear physics is the non-relativistic nuclear physics, is the harmonic oscillator. So fundamentally, there's a disconnect right there, because in principle, you need information at the nuclear scale that reaches beyond the cutoff that you've used in your light quark theory. Now, that may be a small correction that you don't have to worry about, but I don't think even people even think about this when they try to do this matching. So indeed, I believe this connection between a light quark interaction and the nuclear physics is very complex. And you don't want to necessarily force nuclear physics to deal with the Lagrangian that people prefer at the light quark level. We don't particularly like to deal with a tensor force between point nucleons. And yet that is the choice that folks who've developed chiral EFT have made. It's not the most efficient choice when you get to the nuclear scale.
Okay, no, I see your point, Vic. I do see your point. But there are cases, maybe this is to be done. Okay, so the case of beta decay, for example, I think it's an example where I think for many years it was missed by just not going to the next step of quarks, which was a simple step, because these are currents, right? The bilinears is a relatively. It led to, I think, to misconception in the field, including the experimentalists. But I agree with you that, yeah, in reality, going from quarks to nuclei is still an open problem, right? So, yeah, so.
Okay, so we're a couple minutes after the top of the hour here, so perhaps now is a good place to stop the slightly more formal discussion and then transition to even more informal, and I'll also stop the recording. But let's thank Wouter one more time for a very lovely talk and lovely corresponding discussion. So I'm going to stop the recording.